Okay, so we're gonna look at the formal definition of a limit. So everybody close everything up. You don't want to, this is one you don't want to miss, because it's otherwise this will be pretty bizarre to you.
Are you recording? Are you recording?
And I am recording. Thank
thing
you for
is
checking.
on the
That's
side.
essential, because I'm famous for that, as you well know. So let's look at the informal definition of a limit here. We know about this, right? We just write it this way. We would just say the limit of f of x as x approaches infinity equals L, for example, right? And that's, you know what, that's probably a bad one to put up there. I'm gonna change that right away, because we're not really looking at infinite limits in this case. You can apply what we're talking about today to infinite limits, but I don't think I'm gonna do that. I think we might come back, that's another one of those topics I'll file away for the end of the year if we have time. But in my opinion, it's maybe not essential. This is not something you're gonna use. What we're talking about today is not something you're really ever gonna use in calculus. It's one of those things where it just defends and tightens up it's kind of the fine print at the bottom of the page, which allows us to do limits the convenient, informal way we've already practiced doing them, right? So this is not something in practice you really, really ever use. But it's something that is good to see, because it's a part of the body mathematics that if you're a mathematician, it's just part of the whole picture that you need to understand. So this is really just more, in my opinion, of, it's not that it, in and of itself, is so hugely valuable. It's not. But it illustrates how in mathematics there is a formal approach to proving that things are the way they are, right? And that's a critical part of it, because mathematics is built up primarily on this idea of deductive reasoning and this proof, where you start with these bedrock axioms and you build up from those, and everything is built on solid foundations, and then therefore you can have some confidence that what you're doing is okay to do, that it's mathematically allowed. So this is one example of how we do that. It's really unimportant that what the example is. It's just the process that I think is more important, if that makes sense. Okay, so let me change this just a little bit. Let's do that. Okay, that's better. So we'd say the limit of f of x as x approaches c equals L, right? And normally that would be a number and that would be a number, right? And that's some function. Really, the way that if we want to be a little more precise about it, even our informal definition gets a little bit more rigorous. We'd say if f of x becomes arbitrarily close to a single number L as x approaches c from either side, then we say that the limit of f of x as x approaches c is L. Okay? So right away, let's kind of talk about what that means. What does it mean to say if f of x becomes arbitrarily, and that is a hugely important word here, becomes arbitrarily close to a single number L as x approaches c from either side? What do we mean by that?
It doesn't actually get there.
Okay, it doesn't get there, true, and that's part of that's part of what we know about limits. Well, f of x actually could get to L. That's possible, right? But x approaches but never gets to c. Okay, so really that never getting to part is the blue statement. But if we're still looking at this red statement up here, what do we mean by if f of x becomes arbitrarily close to a single number L?
We're gonna get like L negative or L positive.
Okay. I mean, now we're starting to flirt with, we're moving kind of in the right direction with this a little bit. What does L positive or L negative really mean?
Just
How much?
infinitely small.
Okay,
Closeness.
an infinitely small closeness. Okay, I'm liking this, we're getting better. And it doesn't even have to be necessarily infinitely small. We can establish how close do we need it to be. But if we say it can become arbitrarily close, is there any limit to how close we can get?
Yeah.
That's the point. That's what arbitrarily close means here, right? We can get as close as we need to by simply doing what with our x?
Maybe approach C.
Approach C even more closely, right? So you get the relationship here. I can always get as close as I need to my limit L by simply just getting closer to C. If that's the case, then the limit works. If that relationship doesn't hold, then the limit falls apart. Okay? So if we look at that kind of in terms of a picture, well, what's that mean? That means that we're going to do something like this. We want to have some value C. So that's down here, it's blue. There's some value C. And as I approach C, the value of the function approaches L. And if I want to get within a certain accuracy of L, all I have to do is walk closer to C, right? How are we going to say that mathematically, though? Right? Mathematically, that's way too informal a language, right? Math doesn't work that way. That's way too ambiguous. Didn't we do the little telephone thing in here at the start of the year? I think we did. I mean, yeah, we don't want that kind of language. We want mathematical rigor in our language. So here's how we can say this. We can say, let f be a function defined on an open interval containing C, right? It doesn't have to be defined at C, but it has to be defined on some open interval containing C, right? And we've seen lots of examples where the function might have a hole at x equals C, but we still can take a limit, right? And let L be a real number. So that obviously we want to be able to approach some value that's corresponds to a real number, right? It can't be infinity or something crazy like that, right? So the statement, the limit of f of x as x approaches C, should say, equals L, means that for each epsilon, so when we say something like that in math, for each epsilon, we're just going to define some quantity called epsilon that's positive, right? For each epsilon that's greater than 0, there exists a delta, and these are just, epsilon is just like a Greek e, and that's a lowercase Greek e, and that's a lowercase Greek d. Delta is greater than 0, such that when the absolute value of x minus c is greater than 0 and less than delta, then the absolute value of f of x minus L is less than epsilon. Okay? Now that looks like a lot of mathematical gibberish. What does that mean? The absolute value of x minus
Please
c. What does
excuse
that
interruption.
represent?
Teachers, we do release of sophomores now for bus evacuation at the front of the school, please. Sophomores, bus evacuation drill at the front of the school.
Okay. What does that mean? If we talk about an absolute value like that, what's significant about that?
Well, it means that C can be either bigger or smaller than X.
Okay, bigger or smaller. And if we were to, if we were going to kind of look at the behavior of absolute value for a second, like let's just take, if this is C, what's represented by the absolute value of x minus c? Like if you go back to algebra 2 for a second, and let's take, you saw stuff like this, like you did problems like this. If I had the absolute value of x minus 2 is less than 4, right? You were asked to maybe solve that absolute value inequality. What'd you do? You got to think back a little bit. What'd you do?
Do like plus or minus?
Well, if the absolute value, if an absolute value is less than a number, do you remember that became an and inequality, compound inequality? Right? That's like saying the argument of the absolute value has to be greater than -4 and less than +4.
Oh, yeah.
Right? Does that make sense?
Yeah.
So, what I always talk to my other 2 classes about is how you can't really do algebra with, and we've talked about that in here, you can't really do algebra conveniently with absolute value bars in the equation, right? Because they really make things more complicated. So we always want to trade the absolute value inequality for two regular inequalities that we
Yeah.
can do normal algebra on in the form of a compound inequality. And then if we contrast that with, not that this is important to us right now, but if we did the absolute value of x minus 2 is greater than 4, that'd be an or statement then, right? Yeah, so whatever's inside then, the argument would have to be greater than positive 4, or whatever's inside would have to be less than negative 4, right? But we're not really dealing with that now, we're dealing with a situation like this, right? So, now what? What's the only thing I have to do to solve for x then?
You can add
Add 2 to everything?
Yeah.
Okay. Is this ringing a bell a little bit? I know it's been a
Yeah.
while. I mean, I get that this is not something you thought about in a while. So we get x, we get negative 2, and we get 6. Okay, make sense?
Yeah.
So see if you can see a correlation here now. If we graph this solution, we've got boundaries at negative 2 and at 6. Those are endpoints, I should say. And here's what the graph looks like, right? Okay, what's significant about 4?
It's
included.
It's not only is it included,
It's not
it's the center, isn't it? It's the center of the distribution, right? No, is it 4? Actually, it's not 4.
No, it's not.
It's 2, sorry, 2.
I was.
2 is the center of the
I just
distribution.
confused.
Oh, sorry, my bad.
Yeah.
So 2 is the center. What about then, what's the distance from 2 to 6?
That's
4.
Or from negative 2 to 2? That's 4, right?
Yes.
Okay, well, those numbers show up, don't they?
Yes.
Is it an accident that the 2 shows up there?
No.
No, it's not. It's not. I mean, really, there's another way we can look at this completely. The 2 is showing up there and the 4 is showing up there, and it's not an accident, is it? We can even show that. Like if I take the function, I love this about math. There's so many different ways you can approach these problems, and they're all completely consistent. And every time, even now, every time I do it, it's kind of, I don't know, it's kind of, wow, that's really cool. I mean, this is not surprising, but it just always reinforces how self-consistent math is. It's bizarre that it is the way it is. Nothing else in the world is like it. So if we were to do, what if I took the parent function, p of x, equals the absolute value of x? Here's another way to look at it. What have I done to that parent function? What did I have there, a minus 2? Yeah. How did I transform my parent graph? If I'm subtracting 2 from x. No, that'd be outside the graph, right? Outside the function.
I think 2 was right.
It goes right by 2.
Yeah.
Everybody agree? So what have I done? I've taken this parent graph, and all I've done is I've split it 2 to the right, like that, haven't I? Right? Okay, so then it makes sense that if I'm looking at, I want to know where an absolute value graph is less than, say, 4. So there's the line. That's supposed to be blue. Y equals 4. Well, what's the intersection of that? What are all the values of x where the graph is less than 4? Oh, it's going to be everything from, well, I mean, I guess I probably didn't draw this right, did I? It should have been back. It should have been back. That should have been higher, right? If that's 2, then 4 should have been up there. We don't have to do that. That's confusing. I want to sort of match a little bit, please. So that's like 1, 2, 3, 4. So there's my line, y equals 4. If I want to find all the places where the function is less than 4, then wouldn't that be just there, up to, over there somewhere, right? Yeah, from negative 2 to 6, right? Okay, and why am I showing you these umpteen ways of doing it? Well, doesn't this make sense then that clearly
At this time,
when
we
we do
need the
that
juniors
translation, I'm just further
to be out
defending.
front for a bus evacuation drill, please. Juniors out front for the bus evacuation drill at this time. Thank you.
We're new.
We're getting evacuated.
Yeah.
Yes.
Don't we know we're doing formal definition when we get stuff? I'm just giving you, I mean, I'm further defending this notion that that has to be the center of the distribution, right?
Yeah.
Because maybe it seems a little hokey to you if I'm just saying, well, is it an accident? You say, well, it could be an accident, right? But it's not, okay? So then if this is gonna be the center of the distribution, and this is just representing the width of the distribution, that's helpful then, right? Absolute value just represents the distance, doesn't it, in this case? So let's go back to our problem. Now maybe this makes more sense. So what does this really mean? This means all the values of x centered on C, right? And the width of the distribution is delta, okay? You get it? So that's gonna look maybe like that, isn't it? It's gonna be everything on the interval centered on C with a width of delta, so it's gonna extend all the way from C minus delta up to C plus delta. Okay?
Yeah.
So that is, I'm not kidding, in math, this is what we call a neighborhood of values. It really is. That's a neighborhood of values surrounding C, defined by delta. Okay? That sounds friendly, doesn't it?
Do you know how many values are in the hood?
Mr. Rogers' numberhood?
Well, I don't know if Mr. Rogers was involved in that or not. He should have been. He wasn't.
The numberhood.
So then all we're saying is that there's gonna be this correlation. We've established, we've got this neighborhood of values of X surrounding C, and we're gonna define the width of that neighborhood by delta, right? That's gonna correspond to something like this. That's gonna correspond to, what does this mean now? You tell me this is the absolute value of f of x minus L is less than epsilon. Well, that's gonna be a region of values centered on what? L, with a width of epsilon. Now, these are the output values, so these are the y values, right? So that's gonna look like that. Get it?
Yeah.
So we're just establishing a connection between this neighborhood of values and the resulting values of the function. And you can almost kind of think about like epsilon as sort of your target accuracy, right? And in that case, this is modeled by even like maybe an industrial process. Like if you're making ball bearings and you know that you need the radius of the ball bearing to have a certain tolerance in order to work in whatever we're building, wheels for cars or something, then you'd need that epsilon. That dictates how much error there can be in that epsilon, for example, right? Well, this limit process then, if we have this limit relationship in this function, then that's gonna dictate how close do we need to be to C for our input variable, right? So maybe a better way to think of it would be like the mass of the ball bearing there's gonna be a tolerance on the mass of the ball bearing, and that's gonna be related to the radius down here that we're controlling when we make the ball bearings or something, right? You get the idea?
Yeah.
Okay? So if this limit exists, then for every value of epsilon, so how wide, every value we choose for our target accuracy around L, there's gonna exist some delta that's gonna ensure that we hit our target, right? We can specify a width of the neighborhood defined by delta that's gonna make sure we hit our target accuracy. Okay? That's the formal definition of a limit. So what can you do with that? Well, I guess before we do something, let's look at some cases where it doesn't work, right? Like, do you see that this is a case where it's really not gonna work well, right? Because, like if we look at this one, I mean, it can work, but it's just doesn't work well, right? If you're very careful about the way you define approaching from the left or the right, you could define a one-sided limit here, and we'll get into that maybe a little later. But you see the problem with this. What is the value, the corresponding value of L? Okay, well, if we approach C, that should probably be L, right? Does that make sense? But that doesn't work very well because as we get closer and closer to C from the right, if we've got some epsilon we're going to define, and let's say this is our epsilon, just arbitrarily. So that's L plus epsilon, and that's L minus epsilon. And we want to be able to get arbitrarily close to our limit L. That's not happening, right? As the ant walks along this function from the right, as he gets closer and closer and closer to C, he's getting further and further and further away from the limit. And so there are values of epsilon that I can't choose a delta for here, right? It doesn't matter, like if I choose my epsilon to be here, no matter, I can get arbitrarily close to C, but I'm never going to get inside my target accuracy, right? The Y values I'm predicting as I approach C from the right are well outside of epsilon. So it doesn't work. There's no limit, which we know because it's a break in the function, right? And we knew that at the outset. Same kind of thing here, right? As I approach C, well, where's the limit going to be? Well, at infinity, right? And so it falls apart right away, doesn't it? As we approach C, there's no way I could ever define some target accuracy that I'm going to get within because the top of the mountain is infinitely far up. So once again, that whole process we've been talking about today falls apart. Same thing here with that infinite oscillation business, right? If this is the value of C, well, if I'm going to define my delta to be, so let's just say maybe that's this is our limit, and we want our epsilon to be like that. It's not going to work. As I approach C, I'm going to oscillate outside of that arbitrary value of epsilon. There are values of epsilon where we simply can't guarantee that as we approach C, we're going to be contained within those, because the function is going to oscillate outside of them. Yeah.
What if epsilon does encapsulate all of the top and the bottom?
Okay, it could, but that's not consistent with our definition, right? Because our definition says for each value of epsilon. So I should be able to pick an epsilon that's arbitrarily small. If this is going to work, there can't be some cap on the values of epsilon I choose.
Okay.
I got to be able to choose 1/1,000,000th arbitrarily and say, okay, now that's got to work. What does delta need to be for that?
Yeah, that makes sense.
Okay. Okay, so now how do we? What are some problems that we could apply this concept to a little bit? Well, this is the kind of stuff you're going to see on your assignment. I just took this off the assignment. So let's look at this one. The function f in the figure satisfies the limit of f of x equals 6 as x approaches 3, right? And we can see that. As x approaches 3, the value approaches 6, okay? Determine the largest value of delta that's greater than 0. Oh, I forgot to mention that too. How come, you can answer this in a second here, but why is it that we say that the distance between f of x and our limit is just less than epsilon, but the distance between x and c in our neighborhood has to be greater than 0 and less than delta? How come? Why do we have to have that greater than 0 there? Think about and who said, Andrew, this is your question, because you said this earlier. What is it about the limits? What's important about C in the limits?
It's the midpoint.
It's the midpoint, but do we ever have to get there? In fact, can we ever get there in our limit? No, we can't, right? The limit does not depend on ever getting to C. In fact, it depends on never getting to C, right? We're approaching C with arbitrary precision, but we never get there. And so the distance between x and C has to be positive, right? It can't be 0, because if it were 0, what would that mean? We got to C, and we don't do that with the limit, okay? You get that?
Yeah.
But could the value of the function equal the value of the limit? Certainly. And here's a really simple example.
Please excuse this interruption. Okay, seniors, please head out to the front for the bus evacuation drill. All seniors to the front for the bus evacuation drill, please.
I think it's pretty easy to
What's the
know.
limit of the
Please
function
return to
here?
class.
2.
2, what's the value of the function?
Two.
Okay, right? So in this case, epsilon is always 0, isn't it, no matter what you do?
They have to go.
We have to go.
Yeah, can we just?
And I mean, it's also pretty
never
easy
know.
seeing our
Yeah.